Hi, welcome back to the P5 series, the probability and statistics series, and specifically for permutations and combinations topic. So in the last video, we discussed year 2012. Today, we're going to talk about 2013. So let's see our first question. Okay, so four families go on a theme park together. Mr. and Mrs. Lynn take their two children. Mr. O'Connor takes his two children. Mr. and Mrs. Hammad take their three children. Mrs. Burton takes her son. The 14 people all have to go through a turnstile one at a time to enter the theme park. In how many different orders can the 14 people go through the turnstile if each family stays together? Okay, now we have how many families? One, two, three, four. We have four families, right? So that means we have four units. Four families implies four units, basically. So one, two, three, four. Now, that means these four can be rearranged in four factorial ways. Now, using how many different people they have in each family, Mr. and Mrs. Lane plus their two children, we have four. Mr. O'Connor takes his two children, so that means we have three. Mr. and Mrs. Hammad take their three children, so that's we have five. Mrs. Burton takes her son, to two people. So all of these can have different arrangements. So 4 factorial times by 3 factorial times by 5 factorial times by 2 factorial. So that's basically this. So 4 factorial times by 4 factorial times by 3 factorial times by 5 factorial times by 2 factorial is just 2. So that would be this. So equals to 8, 2, 9, 4, 4, 0. In how many different orders can the 8 children and 6 adults go through the turnstile if no 2 adults go consecutively? Okay, that means what we have is we have eight children, right? So we have a 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, right? And the adults could go over here. 1, 2, 3, 4, 5, 6. However, we have three more places for adults also. So 1, 2, 3. So how many places for adults do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 places for adults to go. And only 6 adults. So 9p6 basically. Times by the children 8 factorial. So 9p6 times by 8 factorial. That would be this huge value. So 2, 4, 3, 8, 5, 5, 3, 6, 0, 0. All right, now the third part. Once inside the theme park, the children go on a roller coaster. Each roller coaster car holds 3 people. Okay. In how many different ways can the 8 children be divided into groups of 2 groups of 3 and 1 group of 2 to go on a roller coaster? So 2 groups of 3. So basically we have 3 group over here, 3 group over here, and 1 group of 2 over here. So basically we have eight children, so 8C3 for this one. Now we have 5 left, so 5C3 for this group, and then we have just 3 left. No, sorry, 2 left. So 2C2. So 8C3 times by 5, C3 times by 2, C2, that would be 560. And that's the question. All right, so let's see the next variant. All right, so let's see this. A town council plans to plant 12 trees along the center of a main road. The council buys the trees from a garden center which has 4 different hibiscus trees, 9 different jacaranda trees, and 2 different oleander trees for sale. The key word over here is different, different, different. So there's no identical trees over here. All of these 12 trees are different. So if we have the arrangements, these all 12 will be considered unidentical to each other. All right, let's see the first part. How many different selections, that means combinations, of 12 trees can be made if there must be at least 2 of each type of tree? Okay, so first off, we need to list to make sure that we are counting them correct. So we have hibiscus, 2 trees. We have jacaranda, 9 trees. Sorry, no. Hibiscus 4. And oleander trees, we have 2. Now we need at least 2 of each type. Okay, so we're gonna have a list. Since we just have 2 oleander trees, so we can start with 2 for oleander. And let's say we have 4 for hibiscus, so we need um, 12 obviously, so that would be 6. 4 plus 6 plus 2 would be 12. Okay, similarly we can since obviously we cannot add or subtract any value of oleander, so only variations are going to be in hibiscus and jacaranda. Okay, so we just have 4 hibiscus trees, so we can go down. So let's say we reduce 1 hibiscus, add 1 jacaranda, keep oleander 2. Similarly, 2, 8, 2. And we cannot go further beyond this because we need at least 2 in each one. All right, so these are the combinations that we can make over here. So let's write their corresponding scenarios for the combinations. We have 4 hibiscus trees, so 4C4, 9C6 times by 2C2. Similarly, 4C3 times by 9C7, 2C2. 4C2, 9C8, 2C2. All right, so now let's calculate their values. 4C4 times by 9C6 times by 2C2. We get 84. Now 9C7 and 4C3, 144. And now 9C8 and 4C2, 54. So total would be the sum of these 84 plus 144 plus 54, and okay, so 54 plus 144 plus 84, that would be just 282. All right. The council buys 4 hibiscus trees, 6 jacaranda trees, and 2 oleander trees. So as you can see, this was this combination over here. how many different arrangements of these 12 trees can be made if the hibiscus trees have to be next to each other, jacaranda trees have to be next to each other, and oleander trees have to be next to each other? Okay, so that means we have 3 units over here. Sorry, so basically we have 3 units over here, 4, 6, and 2, right? So 3 units, that means this, 4 jacaranda trees, because we have, no, sorry, 4 hibiscus. So hibiscus, 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 jacaranda, 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 and oleander, oleander. So these are the 3 units which can be changed over and over. And since all of these trees are different, not identical, we don't have to divide by the identical items. So 4 hibiscus, 6 jacaranda, and 2 oleander. So 3 factorial times by 4 factorial times by 6 factorial times by 2, that would be this, 207360. Now, how many different arrangements of these 12 trees can be made if no hibiscus tree is next to another hibiscus tree? So that means we have jacaranda, sorry, jacaranda, 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 oleander, oleander. So for hibiscus, we have this place, hibiscus, 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 and hibiscus. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. 9 choices or 9 places for hibiscus trees, but only 4 hibiscus trees. So 9p4 basically simply. Okay, so we have 9 places for 4 hibiscus trees. So 9p4 basically. Times by a, we have all of these different trees, 6 plus 2, 8. So 8 factorial. So 8 factorial times by 9p4. 121927680. So that's it. That's your question. All right, so now let's see the 6-3 variant. Okay, so let's see this. There are 10 spaniels, 14 retrievers, and 6 poodles at a dog show. 7 dogs are selected, that means the combination, to go through the final. How many selections of 7 different dogs can be made if there must be at least 1 spaniel, at least 2 retrievers, and at least 3 poodles? Okay, so first off, let's list them. So we have spaniels in total 10, we have retrievers 14, and poodles 6. And what were the conditions? That we have must have at least 1 spaniel, at least 2 retrievers, that means 2 or more, at least 3 poodles. Okay, all right, so let's start with the spaniel 1. So 1 spaniel and retrieve, let's say, let's go with poodle 3 first, and we need 7. So 1 plus 3, 4, 7 minus 4 is 3. So yes, greater than 2. All right, 1, let's change the number now. Let's add the numbers. Let's add 1 more this poodle. That would mean 2 retrievers. Okay, and since obviously the poodles have to be greater than 3, So we cannot go with one less poodle over here. Now, greater than equal to 1. Now I think we can add one more spaniel. A spaniel or 2, that means, let's say we can keep 2 retrievers and 3, 2 plus 2 plus 3, 7. Okay, so like we started with one column. We started with the lowest value of the spaniels and then increased it one by one, and saw what values can be increased or decreased for retrievers and poodles. So these are the possible combinations that we can make. Now let's write their combinations. 10C1, 14C3, 6C3, 10C1, 14C2, 6C4, 10C2, 14C2, 6C3. All right, now let's multiply them. So 10C1 times by 14C3 times by 6C3. We get this 7 to 800. 10C1, 6C4, and 14C2. 13650. Now 6C3, 14C2, and now 10C2. 81900. Now we add them together. So total would be 7 to 800 plus 13650 plus 81900. So answer plus 13650 plus 72800. So 168350. Now, 2 spaniels, 2 retrievers, and 3 poodles. So as you can see, basically this combination. Go through the final. They are placed in a line. How many different arrangements of these 7 dogs are there if the spaniels stand together and the retrievers stand together? So that means there is no constraint on poodles. Poodles can be anywhere. Okay, so we have 3 poodles, but 2 units for spaniels and retrievers. So that means 5 units, right? So we have 5 units. Why? Because we have 2 spaniel, sorry, no, spaniel. We have retriever together, but poodles can be anywhere. So these are 1 unit, but these are free. They can be anywhere. So we have 1, 2, 3, 4, 5 units. And since these are obviously dogs, they are not identical. So we will have 3 units, that means 3 factorial, times by 2 factorial for spaniels and 2 factorials for retrievers. So 2 times by 2 times by 6, 3 factorial is 6. So that is just simply 24. Now, how many different arrangements of these 7 dogs are there if there is no poodle next to another poodle? Okay, so we have spaniel, retriever, but poodle can be over here, over here, over here, and over here. So 1, 2, 3, 4, 5. 5 places or choices for 3 poodles. So basically 5p3. So 5p3 times by 4 factorial. So 4 factorial times by 5p3. So that is 1440. And that concludes the May-June variants. Now let's see the October-November variants. So let's see this next question. A shop has 7 different mountain bikes, 5 different racing bicycles, and 8 different ordinary bicycles on display. The cycling club selects 6 out of these 20 bicycles to buy. Okay. How many different selections can be made if there must be no more than 3 mountain bicycles and no more than 2 of each of the other types of vehicles? Okay, all right. So we will have different scenarios. So let's see. First off, we need to list out how much we have. So mountain bikes, we have 7. We have racing bikes, 5. And ordinary bikes, we have 8. So we can't go more than 2 for each of those. So that means we need to start with 1 and 1. No more than 3, that means it has to be less than equal to 3. No more than 2, no more than 2. All right. And we need to make 6 total. All right. So let's start with 3 for mountain and 1 for racing, 1 for ordinary. We can alternate that also. 2 for racing, 1 for ordinary. And if we reduce the mountain bike by 1, we can have 2 and 2, which is sufficient over here. If we go by mountain bike 1, so since we want no more than 2 or 2, we will not be able to have 6 bikes already. So these are the only possibilities that we can have. All right, so now let's write their combinations. 7C3. Notice that these are different selections and these are different bicycles, so there's no identical item over here. 5C1 times by 8C2. Second one, 7C3, 5C2, and 8C1. 7C2, 5C2, 8C2. Now we just need to find their values and just simply add them together. So 7C3 times by 5C1 times by 8C2, 4900. Then we have 8C1, 5C2, 2800. And then we have all of them too. 2 and 7C3 also. 7C2 also. So 5, 8, 8, 0. Now we just need to add them up. 2800 plus 4900. So total would be 4900 plus 2800 plus 5880 equals to 13,580. Easy peasy. The cycling club buys 3 mountain bikes, 1 racing bicycle, and 2 ordinary bicycles. So basically this scenario over here. And parks them in a cycle rack which has a row of 10 empty spaces. Okay, so 10 empty spaces and we need to park 6 bikes. How many different arrangements are there in the cycle rack if mountain bicycles are all together with no spaces between them? Ordinary bicycles are both together with no spaces in between them, and the spaces are all together. Notice that it doesn't say anything about the racing bicycle because obviously it's just one, so doesn't matter. Okay, now how would we actually go about this? So we have three mountain bikes together, and we have ordinary bikes two together, and we also have one. Sorry, no. Sorry, ordinary. So ordinary racing, and then we have 4 empty spaces. So what's the significance over here? That this is one unit, this is another unit, this is a unit by itself, and these 4 spaces are another unit. So we have 4 units that we have. So 4 units, and in between them, since mountain bikes, all the bikes are different, this is going to be 3 factorial, 2 factorial, and spaces, obviously spaces are identical, so we don't need to do anything for them. So this will go, since we have 4 units, 4 factorial, times by 3 factorial for 3 different bikes, mountain bikes, and 2 different ordinary bikes. Spaces are obviously going to be identical. Spaces are identical. So like wherever they are, will be just counted as one arrangement. So 4 factorial times by 3 factorial is 6 times by 2, 288. Now, how many different arrangements are there in the cycle rack if the ordinary bicycles are each at the end of the bicycles and there are no spaces between any of the bicycles? Okay, so the same scenario, 3 to 1 basically, but ordinary bicycles are at the end. We have mountain, racing, ordinary, and spaces can be anywhere, which basically means that we have this unit over here, 1 unit. Now it could be like these are, we'll call them space, 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 space. So this unit can be over here, over here, over here, over here, and over here. Okay, so there are no spaces in between the bicycles, but that doesn't mean that we cannot place them in between the spaces, the entire unit. So as you can see, we have 5 places for the unit for bicycles unit, and then we have O and O, the ordinary bicycles. These are 2 different bicycles. So we have 2 factorial for ordinary bikes because different bikes, they are not the same bikes. And similarly, we have the rest 4 factorial for the mountain and the racing bikes also. So 4 factorial for mountain, and racing bike. Okay, so it's just simply 5 times by 2 factorial, 4 factorial. So 5 times by 2 times by 4 factorial would be 240. All right, so now let's look at the 6-2 variant. Sorry, my bad. This is October, November. Sorry, this was October, November. My bad. My bad. October, November. All right. Now the October, November 6-2. All right. So let's see this. The 11 letters of the word remembrance are arranged in a line. Okay. So first off, before we jump into this, in the word remembrance, okay, we have three E's, two M's, and two R's. Yeah, and these are obviously they are identical over here. So E's, M's, and R's are identical. Find the number of different arrangements if there are no restrictions. So the first part is easy. Different arrangements would be 11 factorial divided by 3 identical E's, 2 identical M's, and 2 identical R's. So 11 factorial. 3 factorial is 6 times by 2 times by 2. This number 1663200. Find the number of different arrangements which start and finish with the letter M. So we have two M's and obviously they're identical M's, so we don't need to times it by 2. So we have 11 letters, so we have starting with M, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this. Since M's are identical, we don't need to do the 2 factorial over here. No need for 2 factorial over here. No need for that. However, we still have 3 E's and 2 R's in the rest of the 9 letters over here. So 3 E's, 2 R's over here. So we have like 9 places, so 9 factorial. So 9 letters to choose, and 3 E's plus 2 R's are identical. So basically 9 factorial divided by 3 factorial, 2 factorial. So 9 factorial divided by 3 factorial is just 6, 6 times by 2, 12. So 9 factorial divided by 12. 30240. All right. Find the number of different arrangements which do not have all the 4 vowels next to each other. So we have 3 E's, 1 A. So E's and A, this is the unit for the vowels. And then you have 7 rest, 1, 2, 3, 4, 5, 6, 7. So basically, in total, we have 8 units. Then we have 3 E's in vowels unit. Okay. Then apart from that, we have 2 M's and 2 R's over here. So we have 2 M's plus 2 R's over here. So for 8 units, we will just simply have 8 factorial. 3 vowels in the unit, we have 4 factorial divided by 3 factorial simply. But to compensate for identical M's and R's, what we will do simply is this 4 factorial divided by 3 factorial times by 8 factorial divided by 2 factorial, 2 factorial. So 4 factorial divided by 3 factorial is just 4 times by 8 factorial divided by 4. So basically just 4 factorial. So sorry, 8 factorial. So 8 factorial, that would be this value. So now when the vowels are not together, so basically this was when vowels are together. So when vowels are together. Now when vowels are not together, so we will just subtract from the this number. So 1663200 minus 40320. So 1663200 minus 40320. This number 1622880. Now, 4 letters of the word remembrance are chosen. Find the number of different selections which contain no M's, no R's, and at least 2 E's. So we have no M's, no R's. That means we have in total what we have. So from the word remembrance, let's write over here remembrance. So this is gone, this is gone, this is gone, this is gone. So we need at least 2 E's and at least 2 E's. We need 4 different letters. Okay. So from the, how many letters do we have? 1, 2, 3, 4. 4 consonants and 3 E's in total. From this we will have to choose. So when 2 E's are selected, so when 2 E's are selected, the combinations like when 2 E's are selected, basically we have like we're selecting 4, right? Somewhat like this. So when 2 E's are already selected, and obviously these are identical E's. So 2 E's are selected, that means we need 2 more out of the 4 consonants. So we could have like different combinations over here. 4 consonants are B, A, and C. So basically we could have 4C2 simply, right? We just need to have any 2 consonants out of the 4. Similarly, when 3 E's are selected, so the same thing basically. Oh, sorry, no. But we have 3 E's now. Now we just need 1 more, so 4C1. So total would be 4C2 plus 4C1. So 4C2 plus 4C1, that would be just 10 ways. And that's the entire question. All right, so now let's see the 6-3 variant. Okay, so let's see this. Find the number of different ways that the 9 letters of the word aggregate can be arranged in the line if the first letter is R. Okay, so before we jump into this, we have 2 A's, 3 G's, and 2 E's in the word aggregate. So now what we want is R in the front. So R chosen first. So we have 1, 2, 3, 4, 5, 6, 7, 8. So if R is already selected or already placed, then we only need for the 8 left, right? So 8 factorial divided by 2, 3, 2 basically. So 2 A's, 3 G's, 2 E's. So basically 8 factorial divided by 2 factorial is just 2, 3 factorial is 6. 6 times by 4, 24. So 8 factorial divided by 24, that is 1680. Now, find the number of different ways that the 9 letters of the word aggregate can be arranged in a line if the 3 letters G's are together, both letters A are together, and both E's are together. Okay, all right. So that means we have um, 3 G's together, 2 E's together, and 2 A's together also. Is that what we are saying, right? Right. So we have these separate units. And then we have open letters 1, 2, 3, wait, sorry, 7. We just have 2 more. Okay. Okay. So the letters that are left are R and T, basically. So how many units do we have? 1, 2, 3, 4, 5. So we have 5 units. So basically just 5 factorial. However, this R and T could be basically anywhere. So G's, E's, and A's are identical. So we do not need to do divide by 3 factorial, divide by 2 factorial, and so 5 factorial is the final answer. So 5 factorial is 120. All right. The letters G, R, and T are consonants and the letters A, E are vowels. Find the number of different ways that the 9 letters of the word aggregate can be arranged in a line if consonants and vowels occur alternately. Okay, this is also easy. We have consonants G, 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 R, T. Obviously, this is not the only arrangement, but we're just playing around with this. However, for vowels, we can have 1, 2, 3, 4, 5, 6 places for the vowels. Okay, 5 consonants and 3 identical ones. So that would be just simply 5 factorial divided by 3 factorial. But we have 6 places for how many vowels? 4 vowels. So basically that would be 4 factorial Sorry, no. They occur alternately. So basically, that means they are all there's no space between them. So we don't have six places. We have just four places for them. So anywhere they start off with alternately would mean that there is no space between them. So for example, if they take this, this, and this. Similarly, if they take um, this one, this one, this one, this one. So this would be the alternate. So it's not actually four places, it's just four places basically because they're occurring alternately. So 4 factorial divided by, and we have two identical, two A's and two E's, and to compensate with that, we will do this. So total would be 5 factorial divided by 3 factorial times by 4 factorial, 2 factorial, 2 factorial. So 5 factorial divided by 3 factorial would be just 5 times by 4 times by 4 factorial is 4 times by 3 times by 2. One of these can be like cancelled out. So 4 times by 3 divided by 2 basically. So 20 times by 12 divided by 2, so 120 basically. All right. Find the number of different selections of the four letters of the word aggregate which contain exactly two G's or exactly three G's. Okay, so we have a problem over here because we have two A's and two E's other than G's over here. So we are selecting from um, 6 letters, but out of them A's and E's are identical. So we have to make different cases for them. Okay, so let's see how we can actually make that. So for two G's, for example, we can make a table over here for this. Okay, so when you have 0A and 0E over here, so that would mean that we have, notice that the G's are gone over here. So we are choosing from 6, right? So 1, 2, 3, 4, 5, sorry. G's are already selected, sorry, my bad. So G's are already here. So what we need to do simply is find out what these two are. So if there are no O and no A, the rest of the letters are basically just RT. So just 2C2 basically, right? So that would be just 2C2. 2C2. If you have 1A, so if you have 1A selected, so that means you are selecting from 2 but only 1. Similarly, if A is already gone, so 2C0. If 1E is there and 0 A's are there, so if 1E is there, so from the rest of the RT, you are selecting how much? 2C1. If 1A comes, then obviously it's 2C0. We cannot have a combination. Oh, sorry, no. We cannot have a combination with 1E and 2A's. Obviously, that's not going to be possible over here. So, like, we will not, because we just have like two places to fill for this two G's over here, so we cannot have that. two A's and zero A's. So if we have two E's, obviously we don't need to choose any of these over here. Similarly, if you we cannot have that and we cannot have that. So now we just need to add all of these up together. So 2C2 plus 2C1 plus you can like add from the rows and you can add from the columns also, absolutely fine. 2C0, this becomes 4 total, 4. 2C1, 2C0, 3, and 2C0 is basically 1. So basically just 8 uh, cases for 2Gs. Now, when you have 3Gs, now it becomes even more simpler. When you have 3Gs, Gs are selected. So that means you can have one E, you can have one A, you can have R, you can have T over here. So it would be just simple. So basically now you have from R, T, E, or A. So basically you are just selecting one out of these four. So 4C1, because you just have you have one choice to make from four possibilities. So 4C1. So 4C1 is just going to be 4. So total number of ways will be 8 plus 4, 12. Now, uh, that's it. Yeah. So basically, that's it. All right. So this was the year 13. Hopefully next time we will look at year 14. Again, if you feel that you need a little bit more explanation in a certain question, feel free to comment. If you have a specific request, you can also reach out to us. But either way, please subscribe to our channel so you can stay updated to the videos that we're uploading and participate. All right, so see you next week. Bye bye.